All right, today we're going to dive deep, and I mean really deep, underground to solve a fascinating puzzle of pipes, pressure, and, of course, profit. It's an engineering challenge that starts almost a mile beneath our feet.
So, picture this. You've struck a massive oil reservoir, which is great news. But there's a catch. A choke point, way down there, is strangling production. How in the world do you fix a traffic jam when it's 5,000 feet underground? Well, let's figure it out together.
The easiest way to think about this, is like a superhighway. For miles and miles, traffic, or in this case oil, is flowing smoothly. But then, all of a sudden, all those lanes of traffic are forced into a single narrow tunnel. That right there is our deep well bottleneck.
Okay, so what's the objective here? It's pretty simple, really. We want to get as much oil from that deep reservoir up to the surface as we possibly can. More flow means more efficiency, and let's be honest, it means a better return on what is a very, very expensive investment.
So, let's get into the specifics of the problem. To keep the wellbore stable at those incredible depths, a narrow pipe, it's called a liner, has to be installed in the deepest part of the well. We're talking from 3,500 feet all the way down to 5,000 feet. And this liner means we're forced to use a tiny 2 3/8 inch pipe at the bottom. And boom, there's our choke point. So what do? What's the solution? Well, it boils down to a classic engineering trade-off. You could call it a tale of two pipes. We can't change that deep section, that's a given. But what about the thousands of feet of pipe above it?
We've got two main options on the table. Option one is the uniform string. It's simple. Just run that same narrow pipe all the way from the top to the bottom. Easy, standard, but the whole system is held back by that one narrow size. Then there's the alternative, the tapered string. This is the clever one. You use a wider pipe for the first 3,500 feet and then taper it down to connect to the narrow section. It's more complex, definitely more expensive, but could it give us a much, much higher flow rate?
And this, right here, is the million-dollar question. I mean, the tapered solution seems better on paper, but it comes with a bigger price tag and more complexity. Is that extra oil you might get going to be enough to actually pay for it and make it worthwhile?
To find the answer, we can't just guess. We need hard data. And to get it, engineers use this really powerful tool called Nodal Analysis. It sounds complicated, but it's a brilliant way to find a system's sweet spot by basically looking at the problem from two directions at once.
Let me break down how this works, because it's actually really cool. First, you pick a point to analyze, a node. And for us, that's going to be the connection point at 3,500 feet. Then you calculate all the pressure pushing down from the surface equipment. Next, you do the opposite. Calculate all the pressure pushing up from the oil reservoir. Finally, you plot both of those pressure curves on a graph. And the spot where they cross, that intersection, that's not a guess. That is the well's actual real-world flow rate. It's the system's natural balancing point.
Okay, so the engineers went to work. They ran the nodal analysis for the simple uniform pipe. And then they ran it for two different, wider versions of the tapered pipe. The numbers are in. Let's see what they found.
First up, the base case. Just sticking with that simple, uniform pipe from top to bottom. The well produces 900 barrels of oil per day. Okay? 900 BOPD. That's our starting point, our benchmark. Now check this out. We run the numbers for the first tapered option using a slightly wider 2 7/8 inch pipe up top. The flow rate jumps to 1,020 BOPD. That is a really significant increase, a huge jump.
So let's look at this visually. Our base case is sitting there at 900. That first upgrade gives us a big leap all the way to 1,020. But now, look what happens when we try the next size up. Going to an even bigger 3-inch pipe, it only brings production up to 1,045 barrels a day. See that? That second jump is way, way smaller than the first one.
That pattern we just saw in the graph, a big gain at first, followed by a much smaller one, that's our most important takeaway here. And it has a name that's fundamental to pretty much all of engineering and economics. It's called the law of diminishing returns. This analysis isn't just giving us a number. It's showing us a core principle in action. As the source material puts it perfectly, this highlights the law of diminishing returns. It means each upgrade you make provides less of a benefit than the one before it.
Let's just look at the raw numbers of the gain. The first upgrade, going from the base pipe to the first tapered option, gives us an extra 120 barrels of oil. Every single day. That is a huge win. But that next upgrade to the even bigger 3-inch pipe, it only adds another 25 barrels. So yeah, while that 3-inch pipe is technically the highest performer, you have to ask yourself, is that tiny extra gain of 25 barrels really worth the much higher cost and complexity of using all that bigger, heavier steel? Almost certainly not. The smart money, the best engineering decision, is on that first upgrade. And that leaves us with a final thought that really applies far beyond oil wells, right? This whole analysis, it wasn't just about finding the absolute maximum flow rate possible, it was about finding the optimal solution, the best balance of cost and benefit. And it forces us to ask a really critical question in any project we do. When is the good enough solution actually way better and way smarter than the technically perfect one?